Hey guys, welcome back to AP Precalc. This is lesson 1.10. Let's get right into it. So here's a bell ringer for today. Pause the video if you haven't done this yet, because I'm about to go over the answers. So we have a rational function, and we want to know which of the following limit statements is correct. And we're looking as x approaches 4 and -1. So here we know from what we've learned so far that x equals 4 right here and x equals -1 are going to be the zeros of the numerator and denominator. When there's a zero that's part of the numerator but not part of the denominator, this is just an actual zero of the function. Right? If we plug in -1, you should get 0, not positive or negative infinity. So we can eliminate C and D just from that. However, when x equals 4, this is when the denominator is equal to 0, and it's a bottom-heavy linear factor, right? That multiplicity is 1, but it's not seen anywhere in the numerator, so this is going to be a vertical asymptote. Taking a look at this, now we want to find the limit as x approaches 4 from the left-hand side of r of x, and see what this is actually equal to. And to do that, think about the number line, right? We have 4 here, and as we approach 4 from the left-hand side, we can plug in a number that's pretty close to 4, but a little less than 4. So this should be, maybe let's try 3.99, right? If we do that, plug it into the function, we have 3.99 plus 1 over 3.99 minus 4. You should get 4.99 over -0.01, which is equal to -499. This is not going to be our answer, but this is indicative of a really big negative number, so this should be negative infinity, and that is why B should be our answer there. All right, so I know we just did our bell ringer, but a good warm-up is simplifying the following rational functions by factoring and then canceling. So taking a look here, we have f of x equals, and then let's factor. So x minus 2, x minus 1 over x minus 1. We can cancel those, and we're just left with x minus 2. Here, if we factor this, we have x minus 2, x plus 4 over x minus 2. We can cancel those into an x plus 4. And here we have an x, factor that out of the trinomial first. So x squared minus 11x plus 30 all over x minus 6. We can even factor this a little more into x minus 6, should be minus 5 all over x minus 6. You can factor those out, and you're left with x squared minus 5x when you distribute that x. And those should be how we simplify by factoring and canceling out common factors. So why did we do this? Let's take a look at that very first equation, right? If we take a look, we factored it like so, and then we cancel it out an x minus 1 from the top and the bottom, and we're just left with x minus 2. But how would we graph this equation, right? Because we canceled it, but it's not necessarily just going to be y equals x minus 2. It's going to be a graph that looks like this. This is actually that graph right there. As you can see, there's something a little different, right? There's that thing. And so, holy crap, what is that thing? That is, no pun intended, a hole, what we call a hole. All right, so we obviously saw that that graph right there had a hole at x equals 1. I'm just going to sketch a quick graph for us here. So -2. And so that is what that graph looks like, but it has a hole at x approaches x approaches 1, right? As we go to 1 in terms of our x values, we're going to see that this comes across a hole. So how would we write those limit statements, and how do you find it if you're not given the graph, right? Obviously, we know as x approaches 1 from the left and the right-hand side, this is going to approach a value of -1. It's easy to see graphically, but how can we do it if we just had that equation, right? Like this. Well, all you want to do is if we plug in 1, right, into the equation, you get 0 divided by 0, which is bad. This is why the whole even exists in the first place. And so what we're going to want to do is we're going to want to cancel out that common factor and now just simplify this equation into x minus 2. And now we can plug in 1 to get negative 1. And so our two limits would be the limit as x approaches 1 from the left-hand side of, we'll call this f of x, is equal to a y value of negative 1. And what this means is, let me erase all this here, is as we approach 1 from the left-hand side, like so, we're going to come to a y value of negative 1. The next limit that we have is the limit as x approaches 1 from the right-hand side of f of x will also equal negative 1. And this is saying as we approach x from the right-hand side, you're also going to come across a y value of negative 1 there. Now, where do holes occur? Holes will occur whenever a factor is going to be two things. It's either going to be equally heavy or top heavy. And that's pretty simple, right? Basically where it is found in the denominator, but the multiplicity is higher in the numerator where it can cancel out. So when it's equally heavy, it's a whole. Like here at x equals 3 is a whole. And you can cancel it out with the ones in the numerator, right? Easy. When it's top heavy here, x equals 3 would be a whole. You can cancel it out with the one in the numerator. There's still one left over, but that's not giving us any domain errors, right? And now when it's bottom heavy, here x equals 3 is not a whole. It's a vertical asymptote. When you can't cancel it out and that still gives you a domain error, that's where it becomes a vertical asymptote. All right? And so just know when it's equally or top heavy, that factor is a whole. When it's bottom heavy, it's a vertical asymptote. And it has to be seen in the denominator for it to be a whole in the first place. If it's just like, let's say we have x plus 3 over x minus 4, x equals negative 3, and this is just an example I'm making up, is not a whole. X equals negative 3, if you know what it is a 0, right? Because this isn't producing any domain errors, so when the numerator is just equal to 0, but it's not giving any problems in the denominator, it's just a 0. All right, so for example 1, determine the x values of any wholes or vertical asymptotes. Taking a look at each function here, we want to first know that these will appear whenever the denominator is equal to 0. So let's find those values now. 2 and negative 1. And then here, if we factor this, we should factor out an x and then get x squared plus 4. A lot of people want to factor this into x plus 2, x minus 2. It's not. This is not factorable. So x equals 0 would be the only real solution where this is equal to the denominator equals 0. All right? So now let's label each one of these as a whole or a vertical asymptote. At x equals negative 3, this factor is equally heavy, so this is going to be a whole. At x equals 5, or at the linear factor of x minus 5, this is bottom heavy, so that's going to be a vertical asymptote. At x equals 2, this is top heavy, so this is going to be a whole. And then x equals negative 1 is bottom heavy, so it should be a vertical asymptote. And then at x equals 0, this is also bottom heavy because it's only seen in the denominator, so this is going to be a vertical asymptote there. All right, so just as a refresher for vertical asymptotes and wholes, a whole occurs when a factor in the denominator can cancel out with factors in the numerator, and a vertical asymptote occurs when that doesn't happen, right? When you can't cancel it out. So taking a look, here there's a whole at x equals 1 where it is equally heavy And when it is top heavy, right, the degree is bigger in the numerator than the denominator. But there's going to be vertical asymptotes when it is bottom heavy because it's only in the denominator, or the multiplicity is higher in the denominator than in the numerator. Taking a look at the graphs, this is what a hole looks like at x equals 1, and this is what a vertical asymptote looks like at x equals 1. Right? So there's both of those, and then the two limit statements. The limit as x approaches 1 from the left-hand side is 3, and same from the right-hand side, it's 3. But here the two limits would be the limit as x approaches 1 from the left-hand side goes down to negative infinity, and as you approach it from the right-hand side, it goes up to positive infinity there. All right, example number 2. Write a left and right-hand limit statement as x approaches 2 for each of the following functions. So for the first one, right, we have at x equals 2, this is a vertical asymptote. So instead of 2, we're going to want to plug in 2.01 and 1.99, and this is only when it's a vertical asymptote. Plugging that in, right, 1.99 and 2.01, on the left-hand side, which is 1.99, you should get 0.99 times 4.99 all over negative 0.01, which is negative 494. So we can say the limit as x approaches approaches 2 from the left-hand side of f of x equals negative infinity. As we approach it from the right-hand side, this should be 1.01, 5.01, all over 0.01, which is equal to 506.01. So then we can say the limit there as x approaches 2 from the right-hand side of f of x equals positive infinity, because that's basically going to be positive infinity there. So those should be our two limit statements there. So 2 minus and then 2 plus. All right, for B, at x equals 2, this is actually a whole, right? It's equally heavy. And so all you want to do here is just cancel, and now we can plug it in. So if we plug it in, 2 plus 4 is 6, over 2 minus 3 is negative 1. This is negative 6, and that's going to be the same for the left and the right-hand limit statement. So here, the limit as x approaches 2 minus for g of x equals negative 6. And then from the right, the limit as x approaches 2 plus of g of x equals negative 6. And that would be our answer there. For the final one, let's cancel what we can. So we can cancel out an x minus 2 squared, which we're just left with x minus 2 on the top. So here, this simplifies to x minus 4, x minus 2 over x minus 1. We can now plug in 2, no worries, because there's no domain error. So on the left, so plugging this in, right, you then get negative 2 times 0 over negative 3, which should just equal 0. So this is going to be our limit. The limit as x approaches 2 minus of h of x equals 0. And then the limit as x approaches 2 plus of h of x equals 0. And that should be our limit statements for those four there. All right, so one more thing to remember. I know we kind of touched on this before, but it's still really important now that we're talking about the wholes, is when you have a value x for a function that causes the entire rational function to have a vertical asymptote or a whole. So basically anything that makes the denominator equal to 0, then this is not a 0, right? We exclude that from being a 0. It is going to cause a vertical asymptote or a whole, and that's the category it falls into. Likewise, when you see a value that is only making the numerator 0, but is not found at all in the denominator, that's not considered a whole. It's also not considered a vertical asymptote. It is just a 0. All right, so example 3, find the zeros of the following functions. These are just going to be here. We see x plus 3 is in the denominator as well, same with x minus 5. So those would not be zeros. The only zero here is x equals negative 2. And then here we see x minus 2 is in the denominator. X minus 1 is, but that's not up top. So here, x equals negative 3 and positive 4 should be two zeros that we can find there. All right, example 4. For each of the following rational functions, determine and label any values of x where the graph has a whole or a vertical asymptote. So taking a look at each of these, let's find first where are the denominators equal to 0. And then let's factor c as well. So here x equals negative 4 and positive 3, negative 5 and negative 2. And then factoring this, we get x plus 2, x minus 2 over, and then factoring this out, we should get, let's see, 2x, and then an x, and I'm going to go probably x minus 2, or x plus 2, and then minus 3. Yep, would be how you factor that. And so once we have this, we now know our zeros, or what makes the denominator equal to 0 for c, should be 3 over 2 and negative 2. Right? And 3 over 2 you can get by setting 2x minus 3 equal to 0. 2x equals just 3. X equals 3 over 2. And then the other one is pretty simple, x equals negative 2, right? So for A, this one, negative 4, this is a bottom-heavy factor, so that's going to be a vertical asymptote. X equals 3, equally heavy, so that's going to be a whole. Here, x equals 5, equally heavy, so that's going to be a whole. And then x equals negative 2 is only found in the denominator, so it's bottom-heavy, so vertical asymptote there. And then here, x equals negative 2. This is going to be equally heavy, so this is going to be a whole. Then x equals 3 over 2 is only found in the denominator, so vertical asymptote because it is bottom heavy. All right. Example 5. Now we're just getting into a few practice questions of what you could see on a potential test or a quiz. Let h be a rational function whose graph has a whole at x equals negative 4 and a vertical asymptote at x equals negative 5. So this means we want the linear factor of x plus 4 to be either top-heavy or equally heavy. So let's see where that's the case. In A, it's equally heavy, so that works. B, it's bottom-heavy because it's not seen in the top. C, it's top-heavy. And D, it's bottom-heavy, so we can eliminate B and D. Vertical asymptote at x equals negative 5. We now want x plus 5 to be a bottom-heavy factor. So this is only found in C. In A, it's just a 0, not a vertical asymptote there. All right, so for example 6, we have the graph of k of x as that's shown, and we want to figure out where is there a vertical asymptote and where is there a whole. There should be a vertical asymptote where the factor is going to be bottom heavy, and so the only bottom heavy factor is x equals negative 2, which is at x equals positive 2. So we can eliminate B and C just from that. Now we want to figure out where is there a whole, and so that's going to be where is it equally or top heavy, and the only other factor is going to be x plus 3, which is x equals negative 3. And so this should be the whole. So A is the correct answer for example number 6. Example number 7 is looking at graphs and getting the limits from those. So the graphs of f and g are given below. Use the graphs to find the limits. So as x approaches 5 from the left-hand side, this is going down to negative infinity. But as we go in from the right, this is going up to positive infinity. As we approach 6 from the left-hand side, this is approaching a y value of 3. and the same from the right-hand side, right? So at a whole, those limits as x approaches a whole will be the same as it goes from the left and the right-hand side because they're going to meet up at the same y value there. If we take a look here, at x approaches 3 from the left-hand side, this is negative infinity, and 3 from the right-hand side, also negative infinity. As x approaches negative infinity, this is going to go to a horizontal asymptote of 4, and as x approaches positive infinity, this is also going to go towards 4. If you have any questions, please come into office hours, and I will see you guys later. Thanks.